Okay, can everybody hear me all right? Am I coming through? Oh, no, you can't hear me. All right, so we've got some exciting stuff to work on today, and before we get into that, just a couple of quick reminders. Number one, about the research paper. If you do choose to complete that assignment, you can submit it by Friday, the 24th. You can take up to the last day of class if you want to submit that one. It's optional. Homework number 11, though, is not optional, and that's available now on Blackboard. So please submit that before our class on Friday the 24th. That's our last class meeting. And then the final exam is scheduled for Friday the 1st of May, and I'll give you the additional details about that in class next week. Any questions on these announcements before we begin talking about stochastic modeling?
Yes, Dr. Waite.
Yes.
So the final exam, will it be cumulative or everything after exam 2?
I'll give you the information about the final exam next week. Okay, if you look at the course schedule, the schedule shows that we were going to do HEC-HMS modeling today and then stochastic modeling on Monday, but when I took another look at that, I thought maybe that doing the stochastic modeling first would make it a little bit easier for your homework assignment. They'd give you some additional time to work on the homework assignment if you had that stochastic part today. So that's why we're going to switch, and then HEC-HMS we'll take a look at in the lecture on Monday. So let's begin with a little bit of review. And the thing I want to remind you of is how we came to the understanding of how much rainfall or precipitation is going to turn into rainfall excess or precipitation excess. In other words, in the hydrographs that we've been generating, the amount of runoff is characterized by the NRCS method. And so the figure that's shown on the screen, this figure of a rainfall hydrograph, this is a conceptual diagram that's just breaking the rainfall event up into the amount of water that is retained and the amount of water that is running off from a watershed. And so the area under the curve is the amount that's retained. And we could, broadly speaking, divide that up into the two categories of the initial abstraction, which is the water that's wetting the surface of materials and experiencing surface pooling, and then the retained water that is usually thought of as what is infiltrating. And so then the area above this curve of declining potential infiltration, the area above this is the precipitation excess. And precipitation excess is a function of storage. So storage, this variable S, remember, is related to curve number. So in all of the TR55 models and the HEC-1 models that you've been generating using WMS, this concept is working in the background to tell you what's the quantity of water that's going to be running off. And remember, the units of this are units of depth. So we haven't yet defined the timing. We're just talking about the amount of runoff. So during a 4-inch rainstorm, for example, what this NRCS method maybe would tell you is, of that 4 inches, how much is going to actually be a runoff depth. So that's one part of what's going on in the background when we're using WMS. The other part is that we have a model that's defining the timing of the peak. And so it's translating the amount into when that amount occurs. And so you probably remember that we looked at this SCS unit hydrograph, and the SCS unit hydrograph said that the peak is going to arrive at some duration after the midpoint of the precipitation event. And so this shaded area is just referring to the amount of rainfall excess, and so the width of the line is referring to the duration that there's rainfall excess, and then we have a formula that will calculate the lag time, and tell us how long between when it rains and when we see that point of maximum in the runoff hydrograph. And so the rainfall excess amount, which we were looking at here, that tells us of a 4-inch storm, for instance, how much of that is going to run off. Remember that the rainfall excess depends on curve number. And so the way that it depends on curve number is that curve number gives you storage, and then storage is a key parameter in calculating the rainfall excess. So curve number is really important to get right. If we're imprecise with curve number, or if there's uncertainty, then that can get us into trouble and model error. Lag time also depends on curve number. And so on that previous slide, the unit hydrograph curve that I was showing you, lag time is the key parameter that ties together the timing between when it rained and when you see the peak. And so both of these key parameters depend on the accuracy of your curve number. And the reason why I mention it is that these curve numbers are just estimations. If you remember what we've been doing, we've been going to the USDA website, albeit indirectly because WMS does that work for us. It's downloading the guess of what soil is where. And so that's not data that we've gone into the field ourselves and verified. That's not a geologist with a shovel checking every polygon in your watershed. It's just an estimation. And even if we did know exactly what soil was in each location, remember that curve number also varies a lot depending on how rainy or how dry it's been in the period following an event that we're analyzing. So the curve numbers that we usually look at from a table, we consider that average moisture conditions. So antecedent moisture condition group 2 is the typical moisture conditions. That middle row in this table, if we assume that during the growing season within the last 5 days there's been 1.4 to 2.1 inches, and that may be representative of like our design event. Typical rainfall during the growing season, if we're analyzing, say, the 10-year storm, then most of the time preceding that storm, you'd expect there to be between 1.4 and 2.1 inches. But there's some uncertainty there, because if it's been really dry before your design event, then that would bring the curve number down. We would have these curve number conditions where the growing season rainfall depth has been less than 1.4 inches, then we have these formulas that allow us to find out the range of curve numbers. And so that's what we're going to look at today with WMS, is how do we address this uncertainty, and what impact does it have on the height of our runoff hydrographs. So I want to refresh your memory. You've probably seen the normal distribution in lots of different classes and a lot of different contexts. But here we have a normal distribution, and not all data in the universe is normally distributed. In fact, the normal distribution may be the exception rather than the rule. But it's useful just as a concept to illustrate the fact that sometime there may be some middle value about which most of the data is centered or aggregated around, and then the further away you get from that average, the occurrence is less common. And so you can see in this figure that what we're looking at is one standard deviation away from the average value, and one standard deviation on either side of the average. 68% of the observations would fall within that range. And so that's the area under the curve, 68% of the probability within one standard deviation. And if we go 2 standard deviations away from the average, we would expect to see 95% of the observations within that range. And so keep this normal distribution in mind when today, through our activity, what we're going to do is take a look at, for a certain watershed, what happens if we do a bunch of different simulations and we put in a range of curve numbers and a range of rainfall values. because we have uncertainty about each. I've just been talking about curve numbers till now, saying that we don't exactly know what soil is where, and we don't exactly know how wet the soil's been before our storm. And so there's uncertainty in the curve number, but there's also uncertainty in rainfall data. Remember that anytime you look up the precipitation data frequency server, what it gives you is the middle range estimate of the precipitation depth, but also it defines a confidence interval. In fact, I think I was just looking at the frequency server before class, so let me bring that up real quick. And so here is for a location in West Virginia where we're looking at the table. And you'll notice that in bold, it will tell you the average precipitation depth, but we're also given a range of values, and that range is because there's some statistical uncertainty that occurs when you're projecting probability from such limited observation. So what we'll do today is we're going to look at a certain watershed, and we're going to do a bunch of different curve numbers and a bunch of different rainfall depths. And if that sounds tedious, like what if we wanted to do 100 different simulations? That would be very tedious to do manually, but luckily WMS has a tool built in that allows you to do simulation after simulation, back to back to back to back, without having to manually go in and change the curve number and rainfall depth for each one of them. So luckily they've got us covered, and they're going to make things extremely painless. The watershed in question that we're going to look at is a rural area in Ona, West Virginia, and we're going to follow the Bryan Creek area. So I'll guide you into the right location when we start WMS, and in fact let's do that now. So if you have WMS open already, let me drag it over. Okay, so our project area that we're going to work in today, if you begin the wizard and save the project to a location that you'll be browsing, and today it's especially important that you don't save your file in the like your user directory, because that's protected and you will get error messages. Sometimes you get error messages if you do that, but today you definitely will. And so it needs to be in an unprotected directory that is close to the root of the C directory. And so I'd recommend that in the drop-down box, if you don't already have a temporary folder, create just some new folder with this Create New Folder button, pretty close to the C drive. And here I'm going to do Stochastic, and I'm going to call it Class Demo. So this folder is not saved inside of one of my protected libraries associated with the account user. It's rather just on the C drive itself. Alright, so I'm going to call this Stochastic Demo and save. Okay, and then the area of our project we're going to look at, let me bring it out a little bit so you can get the context. Okay, so here's the Huntington area, so maybe the place to start. I'm Ona, West Virginia. Jump to the search location, and then we're going to have to zoom out a little bit. Okay, so begin focusing in on this location, because it's this creek that we want to ensure that we've gotten. So okay, it's all here in the window. So what you should see is Barker's Ridge Road across the top, Cooper Ridge Road bounding in the east. In the west we'll see Webb Cemetery Road. We want to make sure that we have Big Cabell Creek coming in across this roadway junction here. So let me just zoom out again in case you need the context of where that's at. We're just north of the interstate, and then it's these series of parallel watersheds that we're going to want to get in our project area. So when you have this area defined, click OK, and you may have to minimize and then re-maximize to get the the wizard window back up in your screen. The only thing we're going to get from the web is the elevation data. I'm just going to save us the time of downloading the soil type and land use. We'll assume that it's a curve number of 75 to begin with, so that'll save us the trouble. So download the data, resolution of 15 or better. So I'll leave it at the default of 15. That will be fine. And click next. It got the data. It's loaded it. Just since it's already on this screen, I might as well compute topaz, and I suggest you set your flow accumulation threshold to 50. So compute topaz. It has terminated, and so I'll close that, and I'll also close for now the wizard and turn off this elevation map. And what we want to do is drop our watershed outlet just kind of in the middle of this reach of the stream. Okay, so bringing the wizard back up again, we'll drop the outlet in the middle of this reach. And then once that outlet is defined, we can go to the next window and delineate the watershed. And it crunches the numbers. You can see at the bottom it's doing the calculations. It's calculating the flow paths. Oh, it looks like I just barely missed getting it all down at the bottom there. Well, I'm not going to go back and do it a second time because I want to preserve as much time as possible for the stochastic model. But normally we'd need to pan up a little bit or zoom out to make sure that this flat section at the bottom here wasn't indicating that I was missing some of the watershed. So does everybody have their watershed defined and it looks roughly about like this? Jeffrey got the straight line at the bottom, so I'm not the only one who hadn't panned all the way. Okay. So we have a watershed, and if we wanted to do a HEC-1 model, and we do, then we can go to the hydrologic modeling module if we're not there already, and let's use the select basin tool to double click and open up the HEC-1 parameters, and let's manually put in the curve numbers since we're not going to go through the process of calculating that with the land use and the soil type. Let's define some of that manually. So here in the loss method, normally this would be filled in for us, but we don't have to always calculate the soil type. If you're working in the same rural county and you kind of develop a feel over the years that, well, just about everything around here is curve number 69, then when you're doing one of these quick simulations, you don't have to get all the data necessarily. So let's start with a curve number of 75. And so put 75 in for that curve number in the loss methods, and we verify that it is there. And the unit hydrograph method, since we didn't calculate the time of concentration, it's not going to, since we didn't get the curve number, it's not going to automatically calculate the time of concentration for us. So we can force that manually. So here, opening up, now click on Compute Parameters, Basin Data, and we can go to the SCS method and see that that 75 that we just keyed in the loss method is copied over. And now that we've told it which method we want, we have a lag time, and also now we have the lag time in this field as well. So that's defined in our summary down below. The one last thing that we'd want to put in is the precipitation. And so let's use basin average, and I just had that precipitation frequency data server. Let's use a 24-hour storm, and the 10-year, let me just remind myself what I had set up here for us here. So 3.39 to 3.84. I wonder which storm I had in mind. I might have selected a different area. Just for this first simulation, let's use 3.71 inches. And so that would be a 10-year storm, 24-hour duration. So 3.74. Oh, it's in the mountains. I don't think I'd drug it over here to our project area. (10-year, 24-hour, 3.61). All right. So back to WMS. You can just type in 3.61. We could have used get precipitation from web, but we do need to define the series as the type 2 24-hour. Okay. So now we've put in everything we need where we can run HEC-1. And if we go to the HEC-1 menu and do run simulation, then it will run that, give us a normal end, and automatically open up the hydrograph. And if I double click, here we've got our hydrograph. And this is just for the curve number of 75 and the rainfall depth that I typed in, what was it again? 3.61. So here's our hydrograph. But now, what if we've got some uncertainty that we want to characterize? Sometimes this is called sensitivity analysis, where you're looking at how do the inputs that go into the model affect the outputs. You know, is it a linear relationship? Would a 10% increase in rainfall only give you a 10% increase in runoff? Or is there a nonlinearity there? Does a small change in the input have a really big change in the output? And so let's investigate that. Let's do a sensitivity analysis with this stochastic method tool. So across the top here in the HEC-1 model, by the way, let's delete these previous hydrographs so that when we run the simulation again, the old data is thrown away and we're only looking at the results of our new simulation. Okay, so here in the HEC-1 model, we haven't used it yet, but there's this stochastic modeling menu. And so open that, and yours, mine's filled in already, yours won't be. So I think yours will probably begin by looking like this initially, and actually it may be set to 100. Alright, so this is what yours looks like to begin with. You could do as many simulations as you want with this tool. Just it all boils down to how much time you've got. For our first set of simulations, let's just do 5, just to make it easier for us to see what's going on with the hydrograph. So set the number of simulations to 5, and then turn on the define stochastic model. And there's 2 ways we can do this. We can either directly choose what curve numbers we want to use, or we can say what we think the middle value of the curve number is, and then give it some statistical indicators so that it could apply a distribution. And so for example, it can apply the normal distribution, and it will randomly select, it kind of has a built-in random number generator. It will select the curve numbers based on the midpoint you tell it, an upper extreme and a lower extreme, and then the size of the standard deviation. And so you're defining the width of the normal distribution. So turn on define stochastic model, and then this is a very important point. Right now for your base file name, I think it will probably have the folder selected in the project, in the program directory for WMS, and that will lead to an error message. And so you need to change the folder location to that temporary folder that's close to the C drive. Otherwise you'll get an error message because the program folder is write protected. So I don't know why they default to that location, but they're defaulting to a location that they can't read and write to. So I'm going to set that here in my subfolder that I just created, class demo. Alright, this is fine. Just make sure that the file name is in this temporary folder that you've created and you know you can read and write to without getting an access error. Okay, so now click on Add Variable, and you can see that the first variable that we have the option to override is curve number, and the two options are curve number and precipitation. So let's start with curve number, and here, because we had 5 simulations specified, if we scroll sideways, here are the 5 curve number values that it's going to use, and those curve numbers were automatically generated based on the start value, the minimum, the maximum, and then the size of the standard deviation. And so if we want to look at the curve number is going to be centered around 75, which is our typical value, but for this watershed that has type antecedent moisture condition curve number type 2 of 75, it could be as low as 56 and as high as 87. So let me do that. So the minimum could be 56, the high could be 87, and the size of the standard deviation, I guess I don't really have a good feel for what the size of that is. I mean, we can look at the effects by seeing how widely distributed these values are, and the random generator picked one 71, 73, 80. I mean, if I put in 50, you can see that, click the tab button, now we're going to end up with a few of them in the 60s, a few of them in the upper 80s. Here's a 59.9. I don't want to take the time to do 50, so I'm just going to change it to 5 again, and it will once again generate a spectrum of values between 56 and 87 with a standard deviation of 10, and it's fixed around 75. So this is if we use a normal distribution, but we can also manually override that. So if I just wanted to type in the value, so double click in that, and it gives you the opportunity to write it. Let's take a look at what if our curve number is 60, and then press the tab button, 65, 70, 75, and 80. So we're going to look at a range of different curve numbers for this watershed, and rather than using the normal distribution, let's take manual control for this. Now I need to point, there's one thing out here. See where it says key -1? We have to go into the HEC-1 parameters and tell the program to look here for the curve numbers instead of the ones that we have put in before. So we're going to have to type in -1 to trigger the substitute. We'll put a -1 into the usual field where we designate curve number so that it knows to look somewhere else for which curve numbers. So that's why the next step I'm going to do is we're going to go put a -1 in the curve number field. It's because that's the trigger for the program to look here for the curve number values. Okay, so click OK, and then we need to do that exchange for the curve number. So select basin, double click, and then in loss method we're going to change this curve number to a value of -1. And so when the program sees -1 for curve number, it will look in the alternate location for a series of different curve numbers. Okay, so I'm going to pause for a moment. Are there any questions? Did anybody get lost someplace that I need to illustrate again before we execute this model and see what kind of hydrographs we get? Okay, so click on Done, and then in the HEC-1 model, below Stochastic Modeling, we're going to run Stochastic Model. Alright, and this is just kind of a job control type dialog box, and we don't need to make any changes from the default. Let's just click OK, and you'll notice at the top it's saying 2, 3, 4, 5. So it's run 5 different simulations. It says that the runs have finished, and when I click on the close button, it's going to read the solutions. And so click close. I can see that there is a hydrograph there, and actually it's several different hydrographs. We did this model for a curve number of 60, 65, 70, 75. How do I start the model, Jeffrey asks. So the way that you do that is you go to HEC-1, run Stochastic Model, and then click OK. And then when you click on OK, it will begin the running of the simulations. And when it's finished and you close it, then there they are. Did anybody get this same hydrograph? Normally in a classroom I'd be looking for your heads to be nodding that you got it to work. Jeffrey got it. Anybody else get it? Anyone else? James, thank you. Good. Okay, so that curve number variation had a huge effect. Look that, and by the way, you could probably guess which curve number, which hydrograph goes with which curve number. You know, this is going to be 60, 65, 70, 75, 80. You know, the higher the curve number, the higher the runoff. But this sensitivity analysis tells us that the runoff is actually very sensitive to variations in curve number. That if it has been dry conditions, then we may see less than 500 CFS. If it's been especially wet conditions, we may see the runoff coming out of this watershed as high as 1500. So the flow could vary by a factor of 3 depending on how variable the curve number is. Now, of course, if we wanted to export this data, we can follow the same approach that we have before, where you right-click on the hydrograph and then select the export/print and then text/data, and then you tell it that you want to save a file and browse to the location that you want that file saved. So let's see, class demo stochastic, and then I could call that like hydro.txt, save, and then this is particularly important. When you export, you'd want to have a table with points/subsets. And then once that file is exported, then it could be opened with Excel. So let's just take a look and see if we have all 5 of those hydrographs and what kind of format it's visible in. So I'm browsing to the location where I saved that text file just now. It was in WMS, Stochastic, class demo, and I need to change it to show all files. Hydro.txt is the one that I exported. Okay, so open that, and I'm getting this import wizard, and I need to tell it, see those commas? I need to tell it that it is comma delimited. So I turn on the commas, and it looks like it'll come in columns now. So finish. And so this column is time in minutes, and then this column is one of the runoff hydrographs. And so it alternates between time, runoff, time, runoff, time, runoff. And which is which? Well, if you scroll down, you can see that this is going to be higher flow rates, and it's also going to be, so our peak flow rate of 1500, so it's higher flow rates, and so this is the one where the curve number was higher. So it would be, I think we started off with curve number 60, so 60 curve number. This is the column that goes with the 65. This is the curve number where we had 70, 75, 80. So you can kind of just analyze the data and get an understanding of what order it did the simulation. So that's how we can get at the data that comes out. And so this is a really powerful tool. We looked at how we could use it to change curve numbers around. Let's now see about rainfall. Okay, so delete the hydrographs, delete all, and Let's open up the model and go back into loss method and turn off this -1. So let's take it back to 75, which was kind of our baseline assumption. So let's say we're going to stick with 75, and this time we're going to change the precipitation. So change the precipitation depth to -1. And I bet you've got a pretty good idea why we put that -1 value in there. It's going to be, again, our trigger or indicator to the program that we are using a stochastic distribution of rainfall. So in the HEC-1 model, open up Stochastic Modeling and delete this row that has the curve number data in it. And let's add the variable, and in the drop-down box change it from curve number, instead put it on precipitation. Okay, now what precipitation data are we going to use? Let's use a range of 3.39 to 3.84, and that's our 90% confidence interval. It's 3.39 to 3.84. So our minimum is 3.39, maximum 3.84, and our mid value, our middle value, 3.61. So starting value 3.61. All right, let's do 10 this time. Instead of just 5 simulations, let's do 10 simulations. And that way we can see, let's use the normal distribution. Instead of manually doing it, let's just use this normal distribution. Oh, the standard deviation, probably 10 is too large for that. These are all centered around about 3.5. If we change the standard deviation to 0.3, I'm interested. 0.3 inches is our standard deviation. Okay. Yeah, 10, I think it was just kind of nonsensical because the standard deviation being bigger than any of the values or even the range defined by minimum to maximum. So use the standard deviation of 0.3, and then if we look, so we've got 3.67. Now yours is going to be different because this is randomly generated, but it should all be centered around our mid value of 3.61. Okay, so click OK. We've got 10 simulations in the queue at a variety of different rainfall depths, and we can do, in the HEC-1 drop-down box, run Stochastic Model and click OK, and it'll take a little bit longer this time. You can see it's counting through number 4, number 5, number 6, and then when it's been through all 10 and it gives us the message that the model has finished, we click close, open up, and the model is a lot less sensitive to variation in rainfall than it was to variation in curve number. And so you can see that the hydrographs, I mean, they're not all on top of each other, but they're far more tightly packed around a central value than when we had that distribution in curve numbers. James, I saw your question about the standard deviation just now. I didn't notice it earlier, and so we did change the standard deviation. Probably you've already realized that. Let me just delete these hydrographs. So in the stochastic model, stochastic modeling. Okay. So it looks like we were thinking of it at the same time. So standard deviation we had set to 0.3. We had our minimum, maximum. And so now, as our final thing, what we're going to do is we're going to combine both changes in rainfall and changes in curve number into the same model. So we need to open up in our model summary the loss method and set the curve number to -1, and we're also just going to double check that the precipitation is still set to -1. So we're going to override both of them in the same simulation. So -1 curve number and the precipitation -1, and let's make sure it's still type 2 24-hour distribution. Okay, so OK. So we've set the -1 tag for both of those, and now in the stochastic modeling we can add the variable. So we've got one of them set to precipitation, one of them set to curve number. Let's do 100 simulations. So 100 simulations, and the curve numbers, this time instead of manually keying them in, let's stick with the stochastic range. And so the range was from 56 to 87. So from 56 to 87, and the size of the standard deviation, I don't think it would be that big. If our maximum is 87, then one standard deviation is probably going to be more in the spectrum of about 5. Okay, so if you look, it's normal, it's randomly generated a bunch of rainfall values and curve numbers, and so sometimes we'll have a big rainfall with a medium curve number. Sometimes we'll end up with a low curve number and just a randomly generated rainfall. And so it's not always going to be pairing together a big curve number and a big rainfall in the same event, but it may coincidentally, in this Monte Carlo analysis, you just have random pairings of variables. And so here's a really low curve number with a relatively high rainfall depth. Here's a high curve number with a middle rainfall depth. And so if we just go through these, we can see that, yeah, there's 100 simulations. So click OK. And then in the HEC-1 tool, let's do Run Stochastic Model. And when we begin, it's going to start counting through them. And so, like, if you're on the job, this is a good time to go get a cup of coffee, or maybe check your phone, seeing what everybody's doing on Facebook, because the computer's doing the heavy lifting right now. And if you think about, like, what would it take for you to do this manually if you had to go in and change the curve number, change the precipitation amount, and not only that, keep track of what you'd already done. Like, if you're going to try and randomly generate this yourself, you'd have to have like a paper list, and you'd put a check mark next to each curve number and each combined rainfall depth, and then you'd have to manually export each one of them individually to a text file and then combine those text files. It would be incredibly tedious, but luckily WMS does all that for us. Now, we don't have to wait to the very end. If you press the abort button, you can get it to quit anytime you want. And so, you know, I'm through 53 of them, 54 of them. I could wait to the end, or let me just show to prove to you that you can abort and still get some useful data out of it. We've been through 60 now, so I'm going to abort. It did 60 of them, and I can open up the hydrograph from 60 simulations. And so here is now the sensitivity analysis with randomly varying precipitation depths within, they're randomly varying within a range that I've specified and according to a standard deviation that I told it. So I guess it's normally distributed within the normal, it's random. And then the same thing with the curve number. So now we have an envelope. This range of possible values, I think probably you've seen envelopes like this having to do with the current pandemic, where people are predicting, you know, like what's the minimal number of infections they expect could occur, what's the maximal number of infections. And so sometimes in that envelope of predictions, what they're doing is, you know, a random walk like this, where they are combining different variables together to see what sort of extremes and what's the sensitivity analysis. So it is 9:47. We're almost out of time. That's basically what I wanted to show you today, is how to use that stochastic modeling tool. You know, being able to use this and export the data is part of what I have lined up for you in the homework assignment. So just as a reminder, the homework assignment in question is due a week from today. That should give you plenty of time to work on it. When we have our class meeting next week, I will have more information about the final exam for you. But if you have any homework related questions between now and then, just feel free to send me an email and I'll definitely get back to you. That's it for today. Hope you guys have a great weekend. Take care, stay safe. I will see you next time.